acid strength. This is fun. I should do this more often.
You should. It keeps me entertained.
So the strength of an electrolyte, remember what an electrolyte is? Something that forms ions in solution. The strength of it depends on how much it dissociates into ions. So a strong electrolyte separates completely into ions, a weak one does not. Strength of an acid is related to that. The strength of an acid depends on the degree of ionization, this equilibrium. Does it go all the way to the products? It's a strong acid. Does it only go part way? It's a weak acid. Here, we're using a common abbreviation for an acid. There is no element with a symbol A. So what we mean here, HA, is we mean some acid. It's an acid because it's got the H, right? When it loses the hydrogen ion, it becomes A minus. So that's the conjugate base. And so we will often use HA and A minus as abbreviations for, especially for acids whose formulas are kind of complicated and we get tired of writing them. So strong acid ionizes completely, weak acid only partially ionizes. Okay, so how do we tell the difference? You memorize the strong acids. There's only six important ones. Hydrochloric, hydrobromic, hydroiodic. Chlorine, bromine, iodine on top of each other in the periodic table. Nitric acid, perchloric acid, sulfuric acid. Those are the 6 strong ones. Any other acid is weak. Okay? We can also identify acids by how many protons they have, or ionizable protons, hydrogen ions that they could donate. So HCl, it only has 1 H. That's all that it can donate. 1 proton, monoprotic. A diprotic acid has 2. Which of these is a diprotic acid? It even says it on there. H2SO4, right? It has 2 hydrogen ions. Now, it's only strong in the first hydrogen ion, but we don't have to worry about that yet. And then a triprotic acid would have 3. Can anybody think of a triprotic acid? No, hydrochloric is monoprotic. H3, like PO4, phosphoric acid, or phosphorus acid. It's got 3 ionizable hydrogens, triprotic acid. So a strong acid like HCl, we know it's a strong acid because it's in the list. We look at a solution of this, and we say there's virtually no intact molecules because scientists are precise in how they speak about things. And I cannot bring myself to say that there are no molecules that are intact. Because what if there's 1, right? Then that wouldn't be true. So we say virtually none. Practically speaking, no intact molecules. So here it is with, little balls for the atoms. These separate completely. We don't have any of the green and white left together. So when we show a strong acid dissolving in water, we use a single arrow, and this means that the reaction goes to completion, effectively. So it's all going to go over here. So we can predict the concentration of the hydronium ion if we know the concentration of the HCl. Every HCl is going to make 1 H3O+. So if you have a 1 molar HCl solution, the hydronium ion concentration is 1 molar as well. Any questions? A weak acid does not ionize completely. So here we have with the formula, here we have with the pictures again. And what happens here is that some of them, well, in this case, one of them ionized and the others didn't. It's mostly the intact molecule that's floating around in there. There's just a few that would ionize. So when we write this equation, we use an equilibrium arrow indicating that this is a partial ionization. It does not go all the way. So if we look at a 1 molar HF solution and want to know, well, what's the hydronium ion concentration? All we can say at this point is it's less than 1. Actually, it's a lot less than 1, but it's less than 1. We're going to learn how we could predict what it actually is, but we're not there yet. Any questions? What makes some acids strong and some acids weak? It depends on the attraction between the conjugate base and the hydrogen ion. So here we have a strong acid. This is the conjugate base, and it's attracted to the hydrogen ion. And if they stay together really well, then they have a strong attraction. It's going to be a weak acid. Here, that would be the weak acid, strong attraction here. With a strong acid, you have a weak attraction, and so you get complete ionization. It's another one of those two things, and this time they seem backwards of what they should be. Why can't the strong acid have a strong attraction? Wouldn't that be nicer? This is how I think about it. The conjugate base of this strong acid is very self-confident. Knows that it's the conjugate base of an acid, doesn't need to have the hydrogen ion hanging around to prove it. So it's like, yeah, I'm good, you can go off and do your thing. Strong acid lets all of the hydrogen ions go. This weak acid is a bit insecure. It's like people aren't going to know that I'm an acid unless I have the hydrogen with me, right? So it's going to hold on to its hydrogen ions, and it's only going to let a few go. It's a weak acid. I don't know if that helps or not, but that's what happens in my head. The stronger the acid, the weaker the conjugate base. Weak acids form equilibrium. Equilibria. Equilibria have equilibrium constants, right? So the equilibrium constant for one of these reactions is called the acid ionization constant. So here again we have our generic acid HA. It donates a hydrogen to the water, creating A minus and H3O plus. There's an equilibrium going on here. Here we've written it with H3O plus. We can also write the equation using H plus instead. It's a little simpler to write. We don't have to include the H2O. Is the H2O still there? Yes, it is. Aqueous. There's water everywhere. We just don't need to write it down. Okay? So these mean exactly the same thing. Okay? How do you write an equilibrium constant? Products over reactants, right? Concentration of the products, H3O plus times A minus, divided by the concentration of the reactants. HA, why is H2O not there? It's a liquid. Liquids and solids don't change their concentrations, they don't show up in the constants. Looking at this equation, H plus times A minus over HA. The only difference here is that here we're showing that there's a water molecule holding onto the hydrogen ion. So if this equilibrium constant is small, does this reaction favor the products or the reactants? The reactants. How do we even think about that? If this number is small, that means the numerator is small compared to the denominator. Numerator small, denominator big. So the way you would have that happen is if the reaction only went a little bit over here, you made a little bit, and you mostly had this small Ka. If you have a large Ka, that favors the products. So you could say, I suppose, that a strong acid has a Ka of close to infinity, but it's not meaningful, and so we don't talk about acid ionization constants for strong acids because they don't form an equilibrium, right? They just go all the way, essentially. So here's a table from your textbook showing a bunch of acid ionization constants. It's called Ka. Names of the acids, their formulas, their structural formulas, their ionization reactions, and their Ka values. Over here is the pKa value. We'll learn about that in a few minutes. You don't memorize Kas. You look them up. If you need them on a test, they'll give them to you. Okay, so please don't ask me that. Do we need to memorize that table? No, you don't. Okay, we've got 3 panels here, 3 generic acids, generic weak acids. This is HA, HB, and HC. And which acid has the largest Ka? A large Ka is more ionization or less? More. This Ka is the products over the reactants, so the products are going to be bigger. So the reactant is the acid, the colored circle with the hydrogen on it. The product is a hydrogen ion like this, or where'd you go? Here it is. The anion. So which one has more product? B. This one has colors in it, but at least we don't need to know what the colors are to solve the problem. Any questions? Consider these 2 acids and their Ka values. HF, HClO, here's their Kas. Which is stronger? More ionization is more towards the products. Yeah. So which one's stronger? A. We're looking for the bigger Ka. The bigger Ka means that it goes more towards the products than one that's weaker. A strong acid goes all the way, right? So there's degrees of weak acids. There's not degrees of strong acids. You're a strong acid or you're not. So this one's stronger because this number is bigger. And don't let the negatives in the exponent mess you up. Those can play tricks on you sometimes.